Alright, so we're looking at a topology generated by half-open intervals on the real line. And the reason that we're looking at this is the end of part C here, which is thus the converse of proposition 4.5 is false. 4.5 says that any second countable space is separable, and here we're going to find a separable space which is not second countable. Part C will prove that it's separable, part B will prove that it's not second countable. And so while this topology might not be important in and of itself, it's useful in giving us a proof of the fact that 4.5 is you've only got one direction. Okay, so let's start with part A here. So we want to prove that E is a base for a topology in which members of E are both open and closed. So let T be the topology generated by E. Basically what I want to prove is that E is a base. So it says E is a base for a topology T on R. You actually have to prove that this is a base, and that's not like it's sort of automatic, but it's not, well, not really, it's not automatic. We have to prove it. It's not hard, but it's something that you have to prove. It's not just something in the problem statement that you can take for granted. Okay, so let T be the topology generated by E. By proposition 4.4, tau consists, or T, I don't know why I keep doing that. It's just because like tau is Greek T, but this isn't Greek T, it's just a fancy T. Maybe it's uppercase tau. No, I think it's just fancy. Anyways, T consists of unions of finite intersections of elements of E. But if we look at the set E, what happens if we take the intersection of two half-open intervals? So AB intersected with CD, either one of two things is going to happen. This is either going to be the empty set. If these two sets don't intersect at all, then it's going to be the empty set. But if they do overlap at all, then we're going to end up getting the max of A and C as the left boundary and the min of B and D as the right boundary. And this is in E. Thus, T consists of unions of elements of E, which, by proposition 4.2, means that E is a base for T, because proposition 4.2 says that these two things are equivalent. Okay, so we have that's a base for a topology, and now we want to prove that the members of E are both open and closed with respect to this topology. Any half-open interval in E is open in T because elements of T are unions of elements of E. And if you just take an element by itself, then that counts as a union of elements because it's just you take the one element. Okay, so any half-open interval is open, but also if we take if we take the interval from negative infinity to A inclusive, this is the union of all half-open intervals of the form B, C. That's not right. This should be C, A, where C is less than A. And this is in T, because it's a union of elements in E, because each C, comma A is an element in E. And if you take the half-open interval if you take the open interval from B to infinity, this is the union of all sets of the form BC, half-open, where C is greater than B. Again, this is a union of elements in E, and so this union is in T. And so, the complement of AB, well, this is just the interval from minus infinity to A, union with this interval from B to infinity, which is in T. So, the half-open interval from A to B, its complement is open, which means that it is closed. Thus, AB is both open and closed. And this is true for any element in E. And so therefore, E is a base for a topology in which the members of E are both open and closed. So I guess that's sort of interesting. I'm not sure if that fact by itself is directly useful. And also in part B, which we're about to get to, let's see here, it says here, so what we're trying to prove is that T is first countable but not second countable. The first countable part isn't hard, but for the second countable part, I don't use this fact that they give us. I think I end up using the same idea, but I just don't end up using this phrasing. So I don't know if that makes it inefficient or whatever, but anyways, let's just go through with this. Okay, so we want to prove that this is wow, I just forgot what we're trying to prove. Okay, so we want to prove that it is first countable. So given any particular point, you want to find a countable neighborhood base for the topology at that point. So fix some x in R and let fancy n be the set of all half-open intervals qx, where q is a rational number which is less than x. Then n is countable, because each element of n is uniquely determined by a rational number. And so n is in one-to-one correspondence with a subset of the rationals, and thus it's countable. Okay. And obviously, for all v in n, x is in v, because x is the right endpoint of this half-open interval, v, and it's an inclusive right endpoint of an interval. Okay, so now let U be an open set in T such that x is in U. Since E is a base for T, there exists an A and B such that x is in half-open interval from A to B, which is contained in U. Thus, A is going to be strictly less, or A is going to be less than or equal to x, which is less than or equal to B. Alright, is that what I want? Let's see here. Well, no. Here, what I really want is this. I want that A is strictly less than x. And that's true because we have an open endpoint at A. So A is not in this half-open interval here. So A must be strictly less than X. So now choose some rational number Q such that Q is between A and X, which is possible since Q is dense in R with respect to the standard topology. Then we have Q intersect, or the half-open interval from Q to X is in N, and it contains X, and furthermore, this must be contained in A comma B, because B must be greater than or equal to X in order for X to be contained in the half-open interval from A to B. And we already know that Q is strictly, or that A is strictly less than Q, and so half-open from Q to X is contained in half-open from A to B, so this is in U. Okay, and that's what we need for, and obviously the elements of N are open, and this condition that we've just proven, for any open set U containing X, there is an element of fancy N which contains X and is contained in U. That's what you need to have a neighborhood base. And so thus N is a countable neighborhood base for T at X, and thus, come on. Therefore, T is first countable, because that's what it means to be first countable. At every point, you have a countable neighborhood base for the topology at that point. However, for second countable, you need to have a countable base? Yes. So basically, the idea is for second countable, you can have all these countable neighborhood bases, but you should only need countably many countable neighborhood bases in order to get a base for the entire topology. That's sort of the idea here. Let's scroll down a bit. And then, So, now I guess the main idea, well, actually let's prove it and then I'll babble about it. So to prove that T is not second countable, let B, fancy B, be a base for T, any base. Then B must contain a neighborhood base for T at every X in R. So, in particular, for every irrational number X, choose some Bx in fancy B such that X is contained in this Bx, which is contained in, I'll write it here, X minus 1, comma X. Okay, so let's talk about this. So, for every irrational number X, well, do we even need to do this for all the irrationals? No, this holds for every single X in R. We're just going to, because the point is you use the we're going to end up using the uncountability of the irrationals, but we could just use the uncountability of R. And then it's simpler, I guess. Okay, so for every X in R, the half-open interval from X minus 1 to X is an open neighborhood of X. And so then for fancy B to contain a neighborhood base, for T at every point, there must be some open set, or there must be some element in the base which contains X and is contained in that half open interval from X minus 1 to X. Okay? So the only other thing here is I say choose some Bx such that this holds. Okay, so you got to be careful when you use this word choose, because that sort of means that you're using choice. And I think I'm using the axiom of choice here. And in fact, because we're choosing one of these for every single x and R is uncountable, we're not even using the weaker countable choice here. We're just using the axiom of choice. But the thing is, I'm an analyst, so I don't really care too much. I mean, I don't know. I think it's fine to use choice. I guess if you're being technical, then if you can prove something without using choice, if there is a statement which you can prove without choice, and you prove it using choice, then the proof that does not use choice is technically, logically more efficient than the proof that uses choice, because you're saying, because if you don't have to use choice, then you're getting the same result with fewer ingredients, and so that's a measurably better result. However, the thing about choice is, like, we're doing analysis, and in analysis, choice is everywhere. You need choice in order to get a basis for an arbitrary vector space, and like functional analysis is like the study of infinite dimensional vector spaces. So you don't even have bases. You don't even have like a basis. Base, not a topology base, but like a vector space basis. You don't even have. I have to brush up on the details because I haven't done it in a while. But you don't even have a basis if you don't use choice. And furthermore, one of the first things that's talked about in this textbook, where we come up with an example of a non-measurable set, you have to use the axiom of choice. And in fact, there exists a model of, when I say model, this is like a logic term, like in the mathematical logic field. There is a model in which you do not use the axiom of choice, and in which all sets are measurable. So it doesn't really even make sense to study measure theory if you don't use the axiom of choice. So I guess basically the reason that I'm like babbling so much about this is that I don't think it's a big deal that I'm using choice here, even though it's not good practice if there's a way to do this without using choice. But I don't know if there's a way to do this without using choice. I feel like maybe there is, but maybe there isn't. In fact, that's interesting, because if this does have to use choice, then that begs the question, are separable and second countable the same thing? Or are you able to prove that a separable space need not be second countable if you don't assume the axiom of choice? So that's kind of interesting. But I'm going to use the axiom of choice here, and maybe there's a better proof out there, but this is not that proof. Okay, so now that we've used the axiom of choice, so basically the idea here is that if you can phrase something in a way that you don't use the word choose, then you're not using the axiom of choice. So let x and y be in R such that x is not equal to y. This does not use choice because these can be any arbitrary 2 points. Whereas in the previous sentence I said choose a bx, and that's important because we need to have a set to work with. Okay, so choose or so let x and y be distinct elements in R. Assume, without loss of generality, that x is less than y. One of the two elements will be less than the other one, so let's suppose x is a smaller one. Since bx is a subset of x minus 1, x, so bx does not contain any points which are greater than x, and so y is not in bx. And so bx is not equal to by. So thus, what we know is that if we look at the cardinality of the set B, I'm using absolute values here to mean cardinality, then this must be at least as big as the cardinality of all bx's, such that x is in R. Because, well, that's true because the set of all bx's, each bx is chosen from fancy B. And so this is true because of set inclusion. But now this collection of all sets bx, we just proved that given any two distinct x and y, bx and by are distinct. So this set is actually in one-to-one correspondence with the set of real numbers. Since R is uncountable, B is, because the cardinality of B is at least that of R. This holds for any base B of T. And so T has no countable base. And hence, T is not second countable. So there we go. And the real important thing to note here was that for having a countable neighborhood base at each point x, that we had in the first part of this part of the proof, in the first part of part B, once we were given an x, then we could restrict our q's to be rational numbers and get a countable neighborhood base that way. However, in this part, because of the closed interval on the right, we were able to choose open neighborhoods of each point in such a way that we forced this base to have at least one set with an endpoint x for every single real number x. And so that's why we don't have a countable base. Okay, so then the last part is actually pretty straightforward, and that's to prove that the rationals are dense in this in R under this topology. So for all u in tau, there exists a half-open interval AB which is contained in U, or U and T. There exists some half-open interval contained in there because this is a base. And so, if we look at the open interval from A to the average of A and B, this must be contained in A and B half-open, which is contained in U. Since A and then the open interval from A to A plus B over 2, I guess I've been saying half-open interval throughout this entire exercise, and that means half-open with respect to the standard topology, and I guess that doesn't really make sense with the topology T, which we are talking about in this exercise, because these half-open intervals in the standard topology are both open and closed in this topology T. So what I really mean by half-open is just an interval where you've got a parenthesis on the left and a closed bracket on the right. So anyways, since this open interval, again open meaning open parentheses, Since this is open in the standard topology, there exists some Q rational number such that Q is in it's in this open interval. But then this is contained in U. Alright. Hold on. What did I write in my notes? Q is dense. Is this a Q which is in? There we go. Okay, so hence, hence Q is dense in R with respect to the topology T, rather than with respect to the standard topology. So yeah, that's what we wanted to prove. We wanted to prove that Q is dense, and so there exists a dense subset, and Q is countable. So there exists a countable dense subset of this topology, and so the space is separable. So we have a separable space which is not second countable. However, if a space is second countable, then it must be separable. And that's what we were exploring in this exercise, and now we are done.